Today we'll learn about the advanced encryption standard. Just a word of disclaimer, advanced encryption standard is not the advance of data encryption standard. Okay, it's slightly different. Let's get into the topic. So apparently AES cipher was presented by Reindahl long back. I don't remember the exact year, but it was long back. And it has 128 bit of data to process, but the key size varies. It uses sometimes 128, 192, and 256 are the different key sizes used by AES. Okay, but the second point is very crucial. AES cipher is iterative, okay, which means same kind of steps are done again and again. Is it not similar to Feastel? No, sir, it is not similar to Feastel. Okay, it processes the data as block of 4 columns or 4 bytes, and it operates on the entire data block in every round. But if you could recall what has happened in your Feastel or DES structure, the actual data block was divided into left and right. Equal halves were created, and then each were processed separately, and then they were XORed, swapped, and so on, if you remember. But here, it operates on the whole of data block in every of the round. So it is not divided, and it also does not follow the Feastel structure, as we are going to see how it works. But apparently, it looks like a Feastel structure, but not necessarily the Feastel, right? So the AES encryption process follows this logic. Okay, on the right hand side on the screen, I have presented the overview of the overall picture of what happens in your AES encryption process, right? So initial plain text, which is taken 128 bits, and the key is also taken in parallel. So the key expansion is a process, all right? So it's not key schedule, but in the case of DES, it was a key schedule where keys were generated, it was contracted, and then expanded, then permuted, and then it was sent in every of the round. But here, a set of 128 bit or 156 bit keys is taken, and then it is expanded. It is expanded, and it is given 16 bytes for every of the round. All right. So what happens? Every of the data block is called as state. Okay, this only for understanding. Okay, it has no very technical significance. Okay, the data value is called as state. All right. So plain text of 16 bytes is taken. It is put as a state. Okay, so there are 16 bytes. All right, so 4 bytes per row logic. Right, it's taken as a state. And then it goes for the initial transformation. So what's happening in the initial transformation? Let's see that. And then after the initial transformation, the whole of the state is, again, it is called as the state, which means the 16 bytes of information, that is 128 bits, is again, it is called as a state. But the values at the state is changed because it has gone through a transformation. So for the transformation, the round 0 key is given. That is again 16 bytes in size. All right. So that is given. Generally, it is the XOR. Then you got the state. And then you go for the round 1 transformation. There are 4 steps, as we are going to see shortly. There are 4 steps in the round 1 transformation. So the initial transformation, you can think about initial permutation. Think about that logic, very similar to your DES. Okay. Now it goes for round function. Okay. In every round, what was happening? Expands and permutation, and then XOR, and then S box substitution, add round key. Do you remember? That's what happening in DES. Something similar to that. There are 4 steps which are happening. All of them put together, it is called as transformation. Okay, so there are 4 transformations happening in one round, and parallelly, the round key is also is granted during that time, and then the output is going for another state. Okay, and then the round 2, round 3, round so, and then you reach round N. And then you got your final state. Okay, the final state is your output, that is your ciphertext. All right, so there is nothing complicated here to understand, but it is a process, step-by-step process, where the actual data goes through a lot of transformation so that you get the ciphertext. All right, so this is what happening in AES encryption process. Sir, is the decryption same? Let's wait. We'll learn about that. Moving on. So in general, the AES structure is the data block of 4 columns or 4 bytes is a state, as I have just mentioned. I'm reading and explaining to you. Key is expanded as array of words. So every of the round key is expanded and supplied, okay, for every of the round. Okay, so it has 9 or 11 or 13 rounds in which, okay, sometimes 9 rounds, 10 rounds, 11 rounds, and so on. But in every of the rounds, as I said, there are 4 transformations happening. What are those 4 transformations? First one is byte substitution. Okay, so one S box is used on every of the byte. We are going to see how it works. Okay, one is substitution. So as we have learned, every of the cipher uses substitution and transposition. Okay, so initially it goes for substitution, byte substitution, and the output is going for shift rows. Okay, you got the state which has got 4 rows. The rows are shifted. This is just to place the values in different places. So first value in the second row, maybe the data at the second row first column may be placed in the third row, second row third column, and so on. Okay, within the row it is shifted, and then columns are mixed, something similar to shift rows. So these all are going for transposition. It is not substitution, it goes for transposition. And then add round key. Please remember, round key is XORed. Okay, it goes through XOR operation with the output of mixed columns field operation. So that is the only place your key is added. Okay, nowhere else the key is added. So what happens? The data block is available as a state, something similar to a matrix structure. It goes for substitution initially. That is the standard way of substituting the values, which we call it as byte substitution. Then rows are shifted, columns are shifted, which means it is rotated this direction and horizontal direction, vertical direction rotation, horizontal direction rotation. So it goes for transposition, and then key is supplied to increase the confusion. A simple XOR operation is given there, so one round of transformation is done. Okay, and then the state goes to the next round, where again this kind of 4 transformations are happening. Round key is added, third round and fourth round, and so on. So in the last round, we miss one of the transformations. We'll see that. Okay, so this is the detailed structure of AES. So we have just seen the generalized structure sometimes back. This is a detailed structure. All right. So what happens? You got your plain text of 128 bits, which is coming as a state, goes to the add round key. So first step is your add round key, as we have seen in one of the slides. Okay, the key is supplied. You go for the XOR operation. All right. And then you go for first round. So in the first round, what happened? You got your substitute byte, shift rows, mix columns. Okay, substitute bytes, shift rows, and mix columns. All right. And then round key is added. So first round is done, second round, third round, and so on. So you go for 9 rounds in the same way. Same operation is carried out, but with different keys. But if you come to the 10th round, if you could see, one of these operations is missing. Which is missing? You got the substitute byte, you got shift rows, mix columns is not there. All right, so please remember, in the 10th round, mix column is not available. All right, okay. So, and then you got the ciphertext. So this is the overall structure of your AES encryption. And parallel, your decryption also happens. All right, you see the output is the ciphertext. Okay, the ciphertext is fed, add round key, but which word is added? The last key which was supplied, which means the key is supplied in the reverse order. Okay, so add round key, then round 1. This is not shift rows, it is inverse shift rows, inverse substitute bytes, and then add round key. Okay, just a reverse of it. Okay, wherever you go, you got the inverse. So in the case of the AES decryption, whatever has happened at the encryption side is done in the reverse way. But that is not the case of Feastel structure or DES. Key is supplied in the reverse way, but the operation is same. But here, okay, you got, shift rows, substitute bytes, and then key. Columns, mix column, shift rows, substitute bytes. That's the way. All right, so it's in the reverse way. But what is the first step? We got the substitute byte, shift rows, mix columns. But here, inverse mix column, inverse shift rows, inverse substitute bytes. So the operation also is substituted in an inverse way. Okay, this is what happening in the case of AES decryption. Okay, so AES encryption we have learned, and we also have learned the AES decryption, right? So some comments just to know more about it. So key is expanded into array of 32 bit words. Okay, 4 bytes. 4 different stages are used as shown. Okay, only add round key uses the key. Please remember, key is not given elsewhere. Only add round key step uses the key. That is also simple XOR operation. Okay, each stage is easily reversible. Okay, you can do the reverse of it because the operation is defined very clearly, and the decryption keys are given in the reverse order as we have seen, and the final round has only 3 stages. So please remember these points so that your diagram, your analysis, anything can be given in a clear way when even for the examinations. Okay, moving on. Yes, this is the structure. So what happens in the case of substitute byte? So this is our substitute byte operation. So it is very important for us to know what's happening in substitute byte, mixed columns and shift rows. So let's look at them, what's happening. In substitute byte, it is a simple substitution of each byte. Very simple, sir. A byte is taken, it is replaced by another byte. Very simple. We are also using SBox. Okay, so it uses a table consisting of 16 cross 16 bytes table. Okay, in the case of DES, you remember the SBox was containing 4 rows and 16 columns. Okay, but here it is 16 cross 16 bytes. It contains all the 256 8-bit value. Okay, so 1 byte value, 256 1 byte values are permitted in the SBox. Okay, how are we going to locate? In the case of DES SBox, do you remember? It takes 6 bits as the input and it provides 4 bits as the output. So first value and the last values are together forming, are used to identify the row, and the remaining middle 4 bits are used to identify the column, and so that you get the 4 bits value as the output. Do you remember that? Yeah, something very similar to that. We go for the substitution byte in the SBox. So each byte is replaced by byte indexed by the row, which means left 4 bits of the input is taken to identify the row. The right 4 bits are used to identify the column. So you go for the row, you go for the column. Where it meets, these two are taken. Okay, so these two intersects at a particular place. So that value is replaced by the corresponding row 9, and for example, your input is 9 and 5, 9th row, 5th column. You got a value, so that is replacing. So here nothing is reduced. Earlier, in the case of DES, 6 bits are reduced to 4 bits, but here it is not the case. Here 8 bits are taken, 8 bits are given as the output. So that's another change if you want to compare with DES. Okay, this is designed to be a resistant to all known attacks. All right. Very simple diagrammatic representation of a SBox. Okay, for instance, you got, this is your state. All right, take a particular byte of value. It has got 8 bits. So left 4 bits are used to identify the row. Another 4 bits are used to identify the column. So whatever value comes here will be taken. That will replace S11. So you will get a S-11 as the new value. Very simple substitute byte, no contraction. All right. So substitution byte example is given. I have explained to you, very simple. Now let's get into the next one. You got the shift rows. All right. So what happens in the case of shift rows? All right. Values of the rows are shifted. A circular byte shift. So you got the state. In every of the state, you got the circular shift. Okay. So first row is kept unchanged. So it is not changed. So you got the state which contains 4 rows. So first row is unchanged. Okay. Second row does 1 byte circular left shift. So in the second row, you got probably first value, second value, third value, and fourth value. Okay. So in what happens in the case of second row, it goes for circular left shift. So second becomes 1, third becomes 2, 4 becomes 1, 1 becomes 4. Simple. Similarly, third row does 2 byte left shift. Fourth row goes for 3 byte left shift. So first row 0 shift, so no shift. Then 1 byte, 2 byte, 3 byte, all circular left shift, which means it's not left shift, circular, so that it wraps around and it engages the vacant place. That's what happening in the shift rows. Very simple, sir, nothing complicated. Okay. So what happens in the case of decryption? It goes for the right shift, because as I said, decryption in AES is exactly the reverse of your encryption, including the key schedule, including the operation. Everything goes in the reverse. Okay. So this is the representation. So you got your state, you got the things here. Just hold on. Okay. So you got the states. So this is your first row, second row, third row, and fourth row. First row is kept unchanged, so it goes as it is, S00, S01, 02, and so on. Here it goes for circular left shift. So S11 comes here, S12 comes here, S13 comes here, S10 goes here. See, very simple, sir. The same is represented here. This is what happening in shift rows transformation. Simple? Yes. What's the third one? It's going to be mixed columns. Now, the data in every column is mixed. How is it done? Okay. So each column is separate, processed separately. Okay. Each byte is replaced by a value dependent on all 4 bytes. Okay. So the shift column is, mixed column is a combination of substitution and transposition. All right. So this is your actual state input data. It is going for a multiplication with this matrix. And then you got the value here. So this is what happening in the case of mixed columns. So values are changed. All right. So this is simple representation. Original value goes for this multiplication to get the output value. This is what happening in the case of mixed columns. Okay. So you got your substitute bytes using S box, shift rows using the value shifted in every of the rows, and then you got the mixed columns. All right. 3 operations. Yes, only 3. Anything more? Add round key. Add round key is a simple XOR. So the output of the state comes, 128-bit key is coming, it goes for the XOR, right? This is what happening in every of the round. So add round key value is just an XOR operation of the input. So this is the whole AES round in a representation way. Don't be worried by looking at the diagram. Why is it very much complicated? It's not that much complicated. You got the initial state, substitute byte, you got the state again, shift rows are shifted here, there, and then you got the state, then you got the mixed column operation, you got the state, and the round key is added with the XOR operation, you got the state. All right, so very simple representation of AES round, a diagrammatic way, but we know in the AES, it has got 4 important operations, substitute bytes, shift rows, mixed columns, and add round key. Okay. In the 10th round, you don't have the mixed column, but all the other operations are there. And the key is also scheduled key is expanded and given. Right. Now, what is pending? Yes, how the key is expanded, which is pending. I think I have a slide for that. How key is expanded. Yes, how the key in AES is expanded. Right. So it takes the 128-bit key and it expands into array of 32-bit words. Okay, for 10 rounds, you should have 320 bits. How much is the input? 128-bit. That is why it is called as expanded. Right. So how the key is expanding every of the round in a single round. So you got your original key value that is taken as the word and how it is converted. Okay. You see W0, W1, and W2. It's not undergoing any of the change. Only W3, the last word, is undergoing a small change. If you understand that, this is the key for one round. Then this will be treated like this, and the next round key will be generated. So key is expanded. Okay. Okay, so how is it done? Look at the third one. This point, in 3 or 4 cases, just XOR. Okay, it is just an XOR with the previous value. Absolutely nowhere, no change. Look at this, look at this, look at this. But in first word in 4 it is having a rotation. It has the S box. It has the XOR round, and then it is XOR back with the first value. This output is taken. So there is a small operation. What are the operation? Rotation, S box, and XOR is all happening. This output comes, it goes for the XOR. All other are a mere XOR with the previous word, no change. Okay, this is how key is expanded. All right. Now, in the case of DES, if you remember the key, there was a perimeter choice, and then the keys were going for a circular left shift. And in every of the round, how many times the key has to be shifted was also given, 1 time or 0 time or 2 time, 1 time, and so on. All right. So like that, key was shifted. But here the values are undergoing a dramatic change. Even the key is going through a ciphertext like of work, and then the key is scheduled for every of the round. Okay, this is how AES key is expanded. Okay, what happens in the case of AES decryption? Decryption is not identical encryption because the steps are done in reverse. But this is not true with DES. In DES, decryption and encryption process is same, key was scheduled in a reverse way. But in AES, exactly everything has to be done in the reverse way. All right, look at this in the case of AES decryption. Where is it? It's here. Yeah, ciphertext is given, add round key, then you got the inverse substituted byte. Put it in the reverse way. Inverse shift rows, inverse mix column, and add round key. Add round key is same. Okay, because it goes for the XOR operation. Everything else is in the reverse, and you also don't have one of the operation, that is inverse mix column is not here, and then you got your add round key to get the plain text. Okay, this is what happening in the case of AES decryption. All right, so that's all I have got for you. But what I thought is just to go ahead once again, probably 1 or 2 slides, and then we'll wind up today's class. All right, so in a nutshell, what we have learned so far today, in AES encryption, you got your plain text, which is taken as the state, right? It goes for the initial transformation, and then 4 transformations in every of the round. There are 10 such rounds, except the 10th round in where the mixed column transformation is not available. Everything else is identical. The decryption process is in the reverse way. Key is also supplied in the reverse way. All right, so this is what happening in the overall structure of AES. You got the encryption process, add round key. It goes for 4 rounds, 4 transformations, substitute bytes, shift rows, mix columns, and then add round key once again, and so on. All right, mix column is missing here to get the ciphertext. Decryption goes in the reverse way, add round key. Key is also supplied in the reverse way. There is a separate key expansion process is going on. Every of the operation is reverse. I'm telling again and again, it is not true with DES where the operation is same, key supplied in reverse, but here entire operation itself is different, so it is not identical. Encryption and decryptions are not identical process. So what happens in the case of substitute byte? The state is taken, every of the byte, okay, in the state is replaced by another value, left 4 to identify the row, the right 4 to identify the column. The corresponding value is taken to replace the specific place. That's what happening in the substitute byte. Example is also given. Then you got the shift rows. First row is left intact, nothing's changed. Second row, it goes for 1 circular left shift, 1 byte circular left shift, then 2 byte, 3 byte, the second and third rows respectively to get the shift rows. In the case of mixed columns, there is a multiplication of matrix. State is multiplied with 2, 3, 1, 1, 1, 2, 3, 1, and so on. All right, to get the output, this is what happening in the case of mixed column, and then you got your add round key. It's a simple XOR operation. So in the case of key expansion, so you got the key expansion methodology or algorithm is available. The specific word goes through a separate process, and then it is XOR with all the other values to get the next state of key. So key is supplied in every of the round. All right, so decryption is not identical. As I said, it is in the reverse of encryption. All right, so that's all I have for you today.